Here for Chem 161, where we'll be looking at periodic trends based on the elements in the periodic table and negotiating that according to electronic configurations and some interpretation of the structure of the atom. Okay, so let's start by determining the electronic configuration for the ground state magnesium element. Okay, so the ground state magnesium element is in the third row at the second column position. And you can start by doing the full electronic configuration. So we know that we want to be identifying that position in the periodic table. And so this should be straightforward for you at this time. If not, please review previous videos. You should be able to determine that this is a 1s2, 2s2, 2p6, 3s2 ground state electronic configuration for the neutral magnesium atom in the ground state again. And in shorthand, we would represent this as a square brackets indicating the next nearest lowest atomic number noble gas. So we kind of go backwards from magnesium, identify neon as our starting point there, and then add the valence electrons here listed as 3s2. Okay, so to help us rationalize atomic radii or size of the atom, we need to think about the implications of how the nucleus, which is at the core of the atom, and how this might act on all the valence electrons. So the best way to handle this is to take a step backwards in our atomic model and perhaps rewind to a planetary model just to help us with this concept. So we'll take a step backwards and think about how valence electrons will exist at the outermost regions of the electron and reside highest up on this energy curve and also be located in the largest and highest energy orbitals. So it makes sense that we would expect valence electrons to be at an outer periphery of the electrons, or of the atom. So I'll list that as valence here. And that all the elements, or all the electrons that are associated with this noble gas core, represented by those in the neon gas core, such as the 1s2, the 2s2, and the 2p6, these are in some inner area. Okay, and so I'll shade this to indicate that. So those are, in that shaded region, those are the noble gas core electrons, represented by, in this case for magnesium, 1s2, 2s2, 2p6. And of course, this could be lower or smaller for different elements in question. In this case, we're working with magnesium. So the valence electrons here, of course, in the outermost periphery here, would be 3s2. Okay. So to rationalize atomic size trends, what we want to do is develop an understanding for how the nucleus, with its positive charge associated with all the protons in that nucleus, how the positive charges in here have to interact past the situation of the noble gas core and finally attract electrons at the periphery. Obviously, the atom size, or the radius of the atom, is going to be dictated by the ability for the nucleus, being positive in charge, to attract the outermost electrons closer to itself. So our ability to transfer that positive charge past the noble gas core and attract valence electrons closer is an important idea. So our approach to this, to put a mathematical equation that's very simple, is to say that the effective nuclear charge is what is sensed by an outermost electron, a valence electron, that has a lower effective charge than otherwise predicted by what we see in the nucleus itself. Okay, so we're going to call the effective nuclear charge for our equation here Z, according to what we would otherwise predict for the nuclear charge based on the atom number, so the number of protons. So Z again is used there. We'll put an EFF here. Note that sometimes this is shown in other textbooks or sources as Z star to indicate that it's not Z but a modified Z. Okay, so we're going to have an equal sign. And we're going to base the effective nuclear charge, a value that we expect to be lower than the starting nuclear charge Z, by taking away something. So we're going to do a simple Z minus something. So we want to have the actual nuclear charge, which we know we can predict based on the number of protons in the nucleus. So that part is easy, but we want to take something away from this. We're going to take away S, which represents the screening of certain charges here. Okay, so we're going to call this charge screened by core electrons. Okay, so in our magnesium example here, we saw that the neon electron configuration indicated that there are a core set of electrons represented by 1s2, 2s2, 2p6. That total of 10 electrons resides in our core electrons. These act to mute the nuclear charge that we know for magnesium, which is simply a total of 12 protons. So they're going to kind of mute that 12 to a lower number. And that's what the right-hand side of our equation here teaches us. So for magnesium, the effective nuclear charge is going to be based on a calculation starting with 12 for the total number of protons, and where you're going to subtract the number of charges associated with electrons in the core. So this is going to be minus 10. This is going to give us an effective nuclear charge of 2. So this 2 value is the number of core protons, okay, at the nucleus, the number of nuclear protons that the valence electron actually senses. Okay, so if the ZFF was very large, we would expect the valence electrons to be drawn in towards the nucleus, and if the ZFF, the ZEFF was modest or low, then this valence electron orbital would not be attracted to that nucleus as much. We use this trick to help us rationalize a periodic trend for atomic size. Okay? So, as you can see here in the atomic radii data, referenced here, showing actual values in picometers, we can see, and the size of the sphere represents that value for the radius information, that there are trends. So in general, skipping, of course, the transition metal block in the periodic table, considering only the main group elements and the alkali metals and the alkali earths and that P block, we see that in general, as we go from left to right, so we go across a period, it appears that the atomic radii of neutral atoms decreases. We see that clearly in the second row. We also see that clearly in the third row. We see that also in the fourth row, etc. So in short, again, as we go from left to right across a row, the atomic radii decreases uniformly, walking from alkali metals all the way to the noble gases. So we want to rationalize this based on this idea for effective nuclear charge, and also consider what happens as we go down a column. And we see here that as we go down a column, the N value is increasing. The N value here is indicating where the valence electrons are. So if we rewind, we know from our energy level diagram that we can predict from the periodic table valence electrons associated with higher N value are at higher energy, higher on this energy level graph, and they are further from the nucleus. So they'd be expected to kind of impact the atomic size, giving a larger atomic radius. Okay, so let's look at that a little bit. So here's that same example for magnesium. We've just covered the idea that the neon noble gas core is what we show to be the screen. So that is this kind of diffuse gray area in our diagram at right that is helping to kind of cancel out, quote unquote, protons in the nucleus that the valence electrons would otherwise be attracted to. So we go from, in the case of magnesium, we go from 12 core electrons without a screen, whereas if we include the neon screen that has 10 electrons, we cancel out, quote unquote, 10 of those nuclear protons, and we only have 2 to attract our valence electrons, that in our case here is the 3s2 electrons shown here and here. So only 2 protons are drawing those in because the protons in the nucleus are otherwise canceled by the core electrons, totaling 10 in the case for magnesium. So at this point, you might pause the video and see if you can predict the core electrons for other neutral elements from the periodic table, starting with what you know for the full electron configuration and, of course, the shorthand electronic configuration to help you with that. Okay, so we introduced this equation just a moment ago. We're going to calculate an effective nuclear charge, starting with what we know based on the number of protons in that nucleus and subtracting some value from that, which is identified by the number of electrons in that core. Okay, in this case for magnesium, 10 electrons. Okay, so to organize that same thought, let's look at the first group. So lithium, sodium, potassium, rubidium, and cesium. Recall that a group is a column in the periodic table. And so the atomic number, of course, is the order in which it appears in the periodic table, starting left to right, reading it like a book. So lithium is the third element in the periodic table, 3 protons. Sodium, again, in the same column, 1 element down from that in the periodic table, 11 protons there. Potassium, 1 down from that, etc. We have the atomic number indicating the number of protons. So without a screening idea, valence electrons would otherwise be attracted to a nucleus of 3, 11, 19, 37, 55 protons. But we now have the idea that the screen generated by the noble gas core will cancel out some of those electrons, and the valence electrons will only see a fraction of that number of protons from the core, from the nucleus. Okay. So with that idea, we can put another table in place. So what are the number of core electrons present that are going to cancel out some protons that would otherwise attract valence electrons? So here's where you need your noble gas electron configuration. And for lithium, you know that this element is 1s2, 2s1. So this electron configuration could be rendered in a shorthand to indicate helium as a duet and a 2s1. So there are 2 core electrons associated with helium, and that's why we see a 2 in this place. Okay, for sodium, the full electron configuration, 1s2, 2s2, 2p6, and 3s1. The shorthand for sodium, one is going to be the 10th element from the periodic table, which is neon, and a 3s1. So the 10th element in the periodic table indicates 10 electrons, as we see here, 2, 4, 6, 10 electrons for the core electrons there. Okay, sorry, I made a mistake there. We need a 1 on the 3s1. Okay, and so the pattern continues. Number of core electrons is identified by the noble gas chosen there. So the number of core electrons here will always be a value associated with the noble gas count from the periodic table. So we can calculate now the effective nuclear charge, the Z star or the Z sub EFF. Remember, we're going to take the number of protons in the nucleus, subtract the number of core electrons, and that is going to give us a number here. So you should be able to predict the last row of entries in this slide to help us with this concept and determine what the effective nuclear charge is. And this is going to be what attracts valence electrons to the nucleus, the nuke. So if this value was increasing, we'd expect the outermost valence electrons to be pulled in tighter towards the atom. If the value is increasing or decreasing, then those valence electrons are going to be able to extend further from the nucleus. So take a minute to think about that, see if you can predict the values for the last row of the table here, and resume the video when you're ready. Okay, so with that, hopefully you were able to predict that our effective nuclear charge is simply 1 in each case. Again, 11 minus 10 is equal to 1. 19 minus 18 is equal to 1. 37 minus 36 is equal to 1, etc. So we've just learned that the effective nuclear charge is approximately the same as we go down a column in the periodic table. So this concept is not going to help us understand and rationalize why there might be down a column. So remember, this is down a column in the periodic table. So in PT, periodic table, this doesn't help us rationalize any trends in the atomic size. The effective nuclear charge is the same. So there's no reason to suspect that the atoms will be smaller or larger based on this idea alone. So if we rewind and go back to the actual data, we see that as we go down this column, the size clearly increases, reflected through the size of the sphere or the actual picometer value here for the atomic radii. So we rationalize the atomic size, knowing what we know about the probability of finding the electron according to where we are finding the valence electrons. So in the case of lithium, the valence electrons are in the n equals 2 case. So that is, the valence electrons are 2s1. The valence electrons for sodium are 3s1. Valence electrons for potassium are 4s1. For rubidium here, 5s1. What we notice is that the effective nuclear charge is equal, so it's the same down this column, so we don't have an argument there, but our n value is increasing. This is the principal quantum number, 2, 3, 4, 5 as we go down the column. As the n value increases, we go to larger and larger s orbitals, and we would expect those to establish the ultimate size of the atom. That is how we rationalize the trend in the atomic radii as we go down the column in the periodic table. Very good. Now, when we look at the situation for a row in the periodic table, we see that the effective nuclear charge increases as we go across the periodic table. So I invite you to take a moment to pause the video and predict the effective nuclear charge as you go across this row here. Do a calculation there quickly and prove to yourself that the Z star, or if you want the ZEFF from previous slides in this video, increases as we go from left to right in the periodic table. You can do this for any of the rows in the periodic table. So this is to say that we expect that the effective nuclear charge will increase as we go from left to right in the periodic table, and this will show that for the same n value for the valence electrons, that we can establish a trend in the atomic radius. So with that information, you should be able to predict, therefore, that as we go from left to right in the periodic table, we have a greater force drawing valence electrons towards the core, towards the nucleus, and that this will bring those valence electrons closer together, even though they may lie in the same 2p or 3p valence situation. Okay? And so this is how we rationalize a decrease in the atomic radii, the size of the atom, as we go left to right within a row. Good. Okay, so with those two ideas, hopefully you can rationalize atomic size as we go down a column and as we go left to right in a period, and establish the size of the atom. So I'm going to skip a few slides here for a second and look at that trend as we put it on top of a periodic table. So we have just talked about atomic radius as a function of a trend in the periodic table. And what we've seen is for the atomic radius to increase, we need to go down a column, or we need to go right to left to increase that atomic radius. Okay. Sometimes it's easy to put these two trends together and simply remember that atomic radius increases as we go from this corner of the periodic table to this corner of the periodic table. Okay? And so that's where these sort of diagonal trends indicated by the non-metallic or metallic character can help put the two kind of vectors for trend and atomic radius together. Okay? We're going to see that sort of diagonal relationship from the top right-hand corner to the bottom left-hand corner of the periodic table in other trends like electron affinity and ionization energy. Okay? So we'll go back to those slides in a moment, and we'll see that electron affinity, that is the energy it takes to kind of apply an electron to a neutral atom to make an anion that is negative in charge, the energy associated with that goes again on the diagonal from corner to corner, opposite corner to corner on the periodic table. Likewise, similar idea for ionization energy. So let's look at those two new terms there to try to rationalize that. So I'll rewind here, and we'll touch on the idea of ionization energy. So the ionization energy is the minimum energy needed to remove an electron to form a cation. We can remove many electrons or one at a time, so it becomes imperative to define the first ionization energy as different from the second ionization energy as different from the third. The first ionization energy is the minimum energy needed to remove the highest energy electron to form a cation. Okay, so here's the sodium element, neutral sodium, and we can look at this as an equation and say we are going to take a neutral sodium atom, we are going to add ionization energy, some value of joules for every atom, and remove the outermost, the highest energy electron. So that is, remove that valence electron in the 3s1. This is the electron we want to remove. You can see here in the planetary model for the atom, it's the outermost electron. We're going to remove it. The products thereafter would be a sodium cation missing 3s0, missing that outermost electron. This has the same noble gas core as neon as we started with. So therefore it's not neon, of course, because the number of protons in here hasn't changed. And as a second product, okay, so this is clearly a different species, unassociated with that sodium cation, we have a free electron. We've knocked this electron out entirely away from that atom. It is gone and no longer associated with the atom. We have formed the ion, so we have applied ionization energy. We can look at trends in the ionization energy as a function of the elements in the periodic table. Okay, so that's our idea for the ionization energy. So we look at that data, and here's the data showing on the y-axis, the vertical, which is the first ionization energy, the energy it requires to remove the first electron from neutral atoms, as kilojoules, thousands of joules, per mole of neutral atoms that we try to ionize. And you can see here in this three-dimensional plot, representing the position of elements in the periodic table, that as we go within a row from left to right, that we generally increase, the bars here are getting taller, the numericals are getting taller. Okay? So it's becoming more and more difficult to remove an electron as we go from left to right. This should make sense to you because we now know that as we go from left to right in a row in the periodic table, it becomes a smaller atom. Valence electrons are closer to the nucleus. Valence electrons, as we go from left to right in the periodic table, are more tightly held by the close proximity of the nucleus. It's going to be harder to remove that outermost electron, higher energy to do so. If we have any additional forces that might help us remove that electron, like the situation where we have paired electrons versus situations where we have all unpaired electrons, like we have in the nitrogen, having its 2p3 valence electrons versus 2p4, the fourth electron in oxygen has a little bit of advantage to leave the oxygen neutral atom because we can remove that electron-electron repulsion situation having two electrons in the same 2p orbital. So those are how we explain the broken trends at this column, the sixth column, group 6 in the main group P block of the periodic table. Okay? And clearly as we go down a column in the periodic table, atoms are getting larger N value, as we see here reflected from 1 through 6. Larger N value for those valence electrons, they are just by default larger orbitals, further from the nucleus, and they're going to be very easy to ionize. So the largest elements that we know of are towards this corner of the periodic table, and they require the least amount of energy to remove the outermost highest energy electron and create the ion. And again, trends are similar when we start from a corner like that and walk across the row, across the period. We expect to have to apply more ionization energy to remove electrons since the atom will be shrinking in size as we go from left to right within a row in the periodic table. Electron affinity is a kind of like the opposite. So this is the energy released by the addition of an electron to a neutral atom to form the anion. Okay, so this is describing how nonmetals like to accept electrons, and we expect for many nonmetals, by adding electrons, they can form the next highest noble gas element from the periodic table as far as electronic configuration. And that would be very beneficial. They complete their outermost shell, taking it from an incomplete valence shell to a complete noble gas, and are able to establish stability that way. So by establishing stability, we release energy, and that's the idea of electron affinity. Okay, so for like neutral chlorine, 1s2, 2s2, 2p6, valence electrons, 3s2, 3p5. There are 7 valence electrons here. This is a 7th column element. So in the p block, if we could get one more electron, we would have 8 valence electrons. That has a full outermost shell that would be rendered more stable. And that's what we see when we form the anion of chlorine to make chloride. We've added that extra electron as reflected here from the top equation. And by adding that extra electron, this chlorine neutral has become the more stable chloride, and we release energy. Okay, so the reactor at this point would get hot as we release this energy. Again, you could ask the question, why isn't this argon, which would otherwise have this electronic configuration? And remind yourself about the number of protons associated with chlorine neutral and chloride. Okay, so let's take a look at trends for electron affinity. Which elements might have the largest electron affinity? Which elements are closest to completing their outermost shell? So that is our elements that are almost at 8 electrons, going to exhibit the largest electron affinity values, the largest energy released, or our elements where we have to add 1 electron to a valence shell that only has 3 of the 8 needed. Are we going to see a lot of energy released there? Think about that, and let's look at the data in the next moments of this video. Yeah, so here's that. So we can look at the data. We notice that much of the data has negative signs. So this is telling us that there's energy lost by the atom. We are missing this energy by the atom proper, so that energy has been released by the atom as we make the ion, as we gain an electron. And so we see here that for elements where we only have to add 1 electron to complete the outermost shell, to go from 7 valence electrons, VE minus, to go to 8 valence electrons, that we have very high values here. Some of the highest from the periodic table are in this area of the periodic table, fluorine being the highest, of course, chlorine very high as well. So the ability to add an electron to fluorine to make fluoride releases 328 kilojoules per mole. That is 328 kilojoules for 1 mole of fluorine atoms that become fluoride ions. 349 for chloride, and similarly a very large number for bromine to bromide, etc. When we add an electron to neutral carbon and simply add an electron in an otherwise empty 2p orbital, but don't complete the outermost shell, there's not a lot of energy released comparatively to the group 7 atoms that we see for the halide series. Okay. In the case of nitrogen, you'll see that the value is actually positive, that we don't release energy by binding an electron, but we actually take a step backwards. The sign flipped to a positive. This is because we've asked 2p3 for the valence electron situation for nitrogen to become 2p4. We've now had to have the valence electron pair up in the same orbitals that were otherwise respecting Hund's rule, and we've now got a pairing of electrons in the 2p, and there's electron-electron repulsion, and we pay the price there and have a positive electron affinity value. So in general, electron affinity values are very large negative values as we go from the bottom left of the periodic table to the top right of the periodic table. And we rationalize that not only based on bringing a complete shell for the valence electrons very close to the nucleus, very little core electrons associated with fluorine, and likewise with chloride. But we also don't have any significant penalties to pay there compared to other otherwise happy situations like nitrogen before and after electron affinity or the capture of an electron. Okay, so that's how we rationalize the transfer electron affinity and ionization energy, as well as atomic radius, knowing things about the N value for the valence electrons, as well as the effective nuclear charge, which modifies the number of protons in the nucleus sensed by the outermost highest energy valence electrons, according to those associated with the noble gas core. Okay, please email me if you're